Okay, so today we're going to be doing scalar line integrals. Before I talk about anything, I had some office hours last night, and uh, we went over a few problems from past midterms, and I kind of noticed that there are lots of problems from 2015 and 2016 that were just really, really, really difficult. I mean, seriously, it was the first I had been looking at them, and I really couldn't do it on the spot, and so I kind of I went to that list of midterm 2 topics, and I kind of made a little note to ones that I said that are too difficult, or just like the difficulty was sort of outside of what you could expect for the upcoming midterm. Yeah, so you can see which ones those are. I think 2 of them were kind of difficult Lagrange multiplier questions. The Lagrange multiplier questions, the system of equations, it's easy enough to set them up, but it can be really difficult to solve them out. So that's kind of what I want to say about that. And there's a leaf blower happening in my neighborhood right now, and I hope it doesn't last too long, and I hope it's not too bothersome. I don't know if the computer is good at blocking that out, but I got my chat open, and we're gonna start today. So this is 6.2. This is the last midterm 2 topic. We will be doing 6.1. That's vector fields, which is a super cool topic, but we will be doing that later, maybe Monday. I've yet to figure out what next week's schedule is exactly going to look like, but basically we're going to be investigating this symbol. It's a single integral along a curve of a function. Whatever that means, I'll explain it in a second. So I kind of want to give some motivation for what kinds of things this type of integral will compute. So I'm going to draw a little picture. I was thinking to myself last night, what's a good way I can explain scalar line integrals? And I thought to myself, let's think about jump ropes, because I remember when I was a kid, I remember as a kid I played with lots of jump ropes on the playground, and to kind of weight jump ropes, one thing they do is they put beads on jump ropes. So where's my text? I like that. Okay, so idea is count or compute total number of beads on a jump rope, knowing the bead density per centimeter. So explain what I mean by this. Okay, all right. So imagine this is kind of a jump rope that I have, and I kind of imagine I cut it into a couple different segments. So I'm going to cut it into a short segment here. I was trying to do red, so I've got my first segment, and I've got a second segment that's a little bit longer, a third segment that's pretty long, and then this last segment. And let's say I say approximately I have in this interval about 400 beads per centimeter. And let's say I also know that this is, let's see what I have. I had like 100, no, that would be so many beads. Let's say, just to make things make sense, let's say it's 4 beads per centimeter, and that first line segment has length, let's say 100 centimeters. Okay, we're going to keep going across. Let's say the second one is about 200 centimeters. And the bead density, let's say I'm starting to use maybe I use a different kind of bead. Maybe I'm using sort of bigger ones. Maybe this is what did I say? The density is 3 beads per centimeter. Over here, let's say I have 2 beads per centimeter. And over here, I've got again 4 beads per centimeter. And again, this is my longest one. Let's say this is 300, and this is 200. So what you can do is just kind of like a Riemann sum, except for something that's a segment that's kind of curvy. So one way you can approximate the total number of beads is you can kind of approximate how much you have in each chunk. So approximately, I have about, well, I'm going to add up. So let's see what the contribution is from this piece. From that piece, I get 4 times 100. That's 4 beads per centimeter times 100 centimeters. I can keep adding. So let's see what happens for the second segment. I've got 3 times 200 plus 2 times 300 plus 4 times 200. This is a good rough approximation of, this is about total number of beads. Okay. And so what we'll be doing today is sort of, as you can see, you might get a better approximation by cutting it up into smaller and smaller pieces. And this is kind of the process of an integral. You see what happens in a limit. So that's really the main idea behind what we'll do today. And that's precisely what this symbol is kind of going to be capturing. The C is describing the exact curve of the jump rope, for example. And the curve might be in 2D, it might be in 3D. And then F is sort of defining some sort of density along that curve. And we're interested in the aggregate value of that function along the curve. You kind of also somehow weight how fast you're going. It's just sort of like the one-dimensional analog of the volume element that we've had in triple and double integrals. So let's go to this next page. It's I'm going to draw the same picture. I'm going to draw it a little more. I'm going to draw the same kind of jump rope picture, but I'm going to up the amount of math I use to describe it. Now we're on page 2. And I'm really going to say that I'm parametrizing this curve. I'm going to call this C, and I'm going to be parametrizing it from the interval A to B. So I'm going to use a lot of abstract math right now, but after we get through the abstract math, we'll just do example after example. So we have so we're going back to parameterizations. So that wasn't over. There was a reason why we did that. So we're parameterizing some R of t. So this is, remember, this has an x of t, a y of t, and a z of t. And it's going from the interval from A to B. So my one endpoint of the curve, this is R of A. And this right here is R of B, okay? And let's say I cut up my interval into lots of very small pieces. And maybe this right here is T0, and I increase, this is T1, and I kind of chop it up until I got a whole bunch of time pieces. This is gonna be Ti. Maybe I'll kind of highlight it in green. Ti plus 1. These are little time slots in the domain of the parameterization. So they're t values between A and B. And so all these little ticks up here in that interval get mapped to different spots on the curve. So maybe right here, this is, R of Ti, and this is R of Ti plus 1. That's not a great, okay, I should be more careful with my subscript because pluses look a lot like t's. So let me just, at least for this last one, I'll put a tail on my t, and that should be I plus 1 in the subscript. Okay. And so I'm going to give a better and more formulaic approximation of the total number of beads. So the total number of beads is approximately a sum. So if I have, like, if I've cut my interval into n pieces, maybe I'll be going from I equals 0 up until n. And what am I going to do? I'm going to multiply the density times the length. Okay, so the density, I'm going to model this by f. So modeled by F, you know, at location, oops. R of ti. Remember, R of ti is telling us where we are in space at that certain time. I'm going to compose my density with the location. I promise if this is a little abstract, or there's too many formulas on the board, I by the end of the class, I hope it should be, you know, after enough examples, you'll see what everything is. Okay. And the length, I got to multiply by this length right here. And so that length, I can write that. I'm going to erase this little curve because I don't like drawing in the lines. That I can describe that actually as a length vector of the length of a displacement vector. So I'm going to write this as the length of a displacement vector where the base is r of ti and the initial point, then the terminal point is r of ti plus 1. So if I want to write that in math terms, that's r of ti plus 1 minus, I'm going to have to move this over. I love this feature, okay, minus r of ti. Okay, and what we'll do is we'll take the limit as n goes to infinity, and we'll get some sort of something that looks like an integral. But what I would really like to do is I'd really like to first unpack this piece right here. I wanna explore what that is a little bit. Yeah, that's what we're going to be doing. I'm going to be flipping the page in a second. Where is the limit again? I have I'll do the limit in a second. I'll give you a preview. It's going to go here. I'm not yet on the limit, but it will be the limit as that top summation, that top limit goes to infinity. Because remember, n is telling you how many of these chunks. So if I were looking at this picture right now, I'm seeing 1, 2, 3, 4, 5, 6. So this would be n equals 6. N equals 100. You'd have a whole bunch of little things. Yeah, and we've yet to take a limit. So I'm just answering a question that's appearing in the chat. That's what I'm talking about. Okay. So what I want to unpack this. I'm going to rewrite this, and we're going to see it's going to be fruitful. So we're going to go to page 3, and I'm going to copy paste. I don't know if I can copy and paste. Here's what if I can learn how to, can I just, no, I don't want to do that. It would be very nice if I could copy. That's Zoom. Okay, sorry. I won't learn now. I'll learn later. Okay, sorry. Here we go. So what we're looking at is this thing. This is r of ti plus 1. This is a displacement vector. This is a length of a displacement vector. Circle everything, then you can copy it to the next page. Oh, okay. Okay. Let me, I don't want to, oops. Let me figure that out later. I don't want to practice new stuff at first, but I'm going to keep writing this. So, let me say this. This is equal to the length of x of ti plus 1 minus x of ti, comma, y of ti plus 1 minus y of ti, comma, I'm really just using the formula for difference of vectors and using their components, z of ti plus 1 minus z of ti. I close that bracket, and I've still got that inside of a length. So that's kind of messy. So what I'm going to do is I'm just going to call this delta x. And this will be delta y. And this is going to be delta z, so that I can keep writing my thing. This is now the magnitude of the vector that has component delta x, delta y, delta z. Okay. And I'm going to do something kind of wacky. What I'm going to do is I'm going to multiply by 1. So you remember, I mean, this is, okay, this is delta x, comma, delta y, comma, delta z times, I got to multiply by something over something. As long as I put the same thing on top and the same thing on bottom, really, I'm just multiplying it by 1, but it will be a helpful thing. I'm going to multiply by delta t over delta t. And then this next step, what's going to happen is delta t is going to come right on in. So now I have the magnitude of delta x over delta t, delta y over delta t, and delta z over delta t. Now remember, okay, so that denominator pulled on the inside because numbers scale nicely with the magnitude, but I still have that delta t on the outside. And if you see what happens in the limit, these things all, as delta t goes to 0, these things all become x prime at t. This becomes a y prime at t, and this becomes z prime at t. This is as delta t goes to 0. And really, as this limit goes to 0, we're really looking at, well, a vector with the 3 derivatives, well, we know that as r prime of t inside the square root. So I kind of forgot about the whole Riemann sum, and I just described this red piece, this blue piece. So I'm going to, yeah, can I do that? Actually, let me try this. Let me try what Serena suggested. So I'm going to do this. Okay. And now I'm just gonna, nope, that was sad. I want to take it to this next page. Lasso tool. Nope, not gonna work. It's not gonna work. I just gotta write the whole summation again. Sorry, buddy. Okay, so we're on page 4 now. And so the Riemann sum equals, it's a sum from I equals 1, 0, it doesn't really matter so much, to n. And then, wait, can I go back a page? I can. Here's page 3. That's basically what we did in this step, such as copy, resize, etc. Okay, I'm gonna practice this in office hours or something like this. So what I'm going to be doing is I'm gonna replace that blue top with that blue bottom that we found. Okay. And then this is f of ti times, this is the length piece. We said this is the length of delta x over delta y. No, that's not right. Delta x over delta t, delta y t, delta z t. Close that, and I've got a delta t. And if as n goes to infinity, our delta t goes to 0, this thing becomes the integral from a to b of f of t times the length of the derivative. Oh, sorry. I did something wrong. I can't just plug in f of t. I've got to plug in f of r of t. So let me erase that. That should have been f of the parameterization of t. This is kind of stuff that we did back when we were doing chain rule, composing a function with the parameterization. So how does that manifest down here? That manifests as f of r of t times the length of r prime of t, and then dt. You can see how each piece becomes what it's down there. And this is called the scalar line integral of the function f along the curve C, parameterized by parameterized by R. That's a C param by R of t. And it's written as, symbolically, it's written as CFDS. And it's kind of similar. I mean, this is, you should look at a symbol like this and tell you this is just a symbolic thing. It's telling you the curve. It's telling you the function to integrate along the curve. And this ds, you can think of that as like d segment, because we've had dv and dA. This is kind of the one-dimensional version. And it kind of makes sense because the single integral is telling you that your domain is single dimensional. It's one dimensional. In the past, we've had a triple integral tells us that tells us our domain is three-dimensional. So this is kind of the picture here. And we also will write ds equals this piece right here. This is ds. And I'll kind of expand on that in a second. I'm about to switch pages. Okay. I'll just switch pages. So that was page 4. Here's page 5. Okay. And so I just want to say something. I want to say more about that ds equals the length of the derivative dt. So what you're seeing right here, this is a function of t, and this is sort of like a differential in the t variable. I mean, it's similar to things we've seen before, as like dA. This is similar to dA in polar. Remember, was something like r times dr d theta. Remember, this is a function of the coordinates, a function of my variables, function of variables, and this is, you know, differentials of variables. And again, similar to dv, which was, you know, rho squared sine of phi, you know, d phi, d rho, d theta, d phi. Again, a function and the differentials. So it's really like, it should remind you of what you've done before. Like when you see the theoretical integral, it always includes this, but when you actually have to compute it, this is how you roll up your sleeves and do a computation. Just like all these, when you actually want to do a volume integral, you pick the coordinate system and then, you know, boom, that's what you got to tack on at the end. So let's do an actual example. I'm going to move on to this next page. This page was just kind of like a connecting things to what we already know. So, okay, let's do this. Okay, so I'm going to say, so here was a problem from OpenStax. This is compute the scalar line integral of f of x y equals y. It's a function. And then along C, where this is upper half of unit circle in xy plane. And I'll say centered at origin. I'm going to draw that C for us. The C, something like this. That's our C. And so let's think of everything we need to do. So we're computing, at the end of the day, we're computing the integral of along C of the function f, and then we got to remember a formula for ds. So we have three pieces basically to assemble the thing. So let's first describe this C with the parameterization. Remember, basically, here's a good thing to note. So always, I mean, to get started, you always got to find a parameterization of C. So to get started, always step 0 is to parameterize C. Okay, and this is something that we've spent some time with a few months ago, but a good parameterization is R of t is cosine of t, comma, sine of t. Remember, this is so that would be our x of t, and this is our y of t. And can people think about, see, now we really have to figure out what the bounds are. This is t is going to go between some a and b. People think about what the a should be and what the b should be, so that I start at the right spot and I end at just the right spot. Let's take a moment to think about what those are going to be. 0 to pi. Yes, good. Yes, because this one right here happens when t is 0, and this right here happens at pi. Exactly. Okay, and that's important. It's important to actually get the bounds right, because you need to get the bounds in your integral correctly. So that was basically probably one of the hardest parts in all of this, was just finding the parameterization. Next step is one of the easier steps, and that's just we need to find f of r of t. So in this case, what does this mean? Well, f was merely y. So wherever I see an x or a y, I've got to replace it with my y of t. So really, what I'm saying is along the curve, f of r of t is merely just sine of t. That was our y of t component. I don't really have to square it, I don't have to do anything, because the function really wasn't telling me to do anything crazy. It's just copy down what the y component is. That's all it's telling me. And then the last thing we'll need to do is we'll need to figure out what the ds is. So we'll need to find the derivative. We'll have to find r prime and take its norm. So I'm going to move over to this next page, and on the next page, what I'll do is I'll copy down the parameterization that we found, which was this. I'm going to copy that. Okay. Let me know if you need me to go back. So r of t is cosine of t, comma, sine of t. And this tells me that r prime of t is, well, cosine becomes negative sine. Sine becomes cosine. And we can see that the magnitude of r prime of t, I'll actually write it out. Remember, this is a square root of the components squared. So I'm really looking at sine squared of t plus cosine squared of t. Well, that's just 1. And so where can I see where I got to? Where can you see? Can you go? Yes. Yes. So right now what we're doing is we're computing this piece. Yes. Okay. And then remember ds, to compute that ds, we just did this. We just computed we computed the derivative, then we computed its norm, its magnitude, and we just found out that was 1. So the equation that we're going to get is ds equals 1 times dt. That doesn't always happen, but it happens in this nice case. So this is thus, we have that ds equals 1 times dt. And so now we have all 3 pieces and can assemble the integral. It's really the when I say 3 pieces, it's like the same 3 pieces as when we were doing triple or double integrals. We figured out the bounds, that's piece 1. The bounds in this case is really playing the role of the parameterization. That's what you get. You get to geometrically figure out what's your region looking like and how do you mathematically describe that geometric region. That's step one. Then step two is convert the function to whatever coordinates you'll be using. And then the third step is to figure out what that differential is. So I'll write this right here. This means the integral of the curve, along the curve of the function f, using arc length, is going to be an integral from 0 to pi. Now we said that the function f is just merely sine of t. And we found out that this ds is a really nice case. It's just 1 times dt. And this is a really simple integral. To integrate sine, that's negative cosine. I'm going to evaluate it at pi and 0. And you can double check that this gives you 2. So you get negative 2 minus negative 1 minus negative 1 or something like that. So that's the answer, and that's what the scalar integral is. And let me just show you, like, whenever you get an answer, whenever you compute an answer like any integral, be that a double integral, a triple integral, or a scalar line integral, you finish and you get some number, is it good to go back and see, does my number make sense? So at the end of the day, we got a positive number. I'm going to show you why that makes sense. So here's that 7, here's page 8. And let me draw again the curve. I did it in green and it was right here. And along the curve, we have different y values. Remember, we're different f values along the curve. So remember, f equals y, and y is how high up you are. So at these 2 points, the function was 0. F is 0 here, and f was 0 there. But at other spots, if you go up, maybe this is here we have, maybe we have something like 1/2, maybe that's 1/2. And up here, you've got 1. So no matter what, but minus these 2 points, this was a 0 point, this was a 0 point, you have positive numbers along the entirety of the curve. And that's kind of, we already could have guessed ahead of time that the integral of f over c is going to be a positive number, which is what we got. We got 2. So that's some way you can always check your work and see if you got something correctly. Okay. So that was that. That's 3. Cool. So I just want to remind, because one thing that we had to do in this problem was to find the parameterization. And it has been a while since we've done parameterization, so I just want to remind you how to do some of the most basic parameterizations. I'm just going to show you 2 of them. So this is a reminder how to parameterize some things. These are going to be some standard objects. So I'm just going to do 2. So the first one is a line segment. Line is like a finite line segment from point P to point Q. If you remember, what you can do is you can write R of T equals, P plus T times the displacement vector P to Q. This is from like a long time ago. And then you're going to want your T value to range between 0 and 1. This is important. That's a very important piece. So the reason why is because, remember, so why this piece? Y 0 to 1, we'll just check if you do R of 0, I plug in 0 for wherever I see T, and that gives me P. And then R of 1 is P plus the displacement vector that the displacement vector takes me from P to Q. This is P plus Q minus P, and that's just Q. And then all points in between 0 and 1 are going to correspond to points between P and Q, and nothing outside. Not like you're not really including these points on the full line, which is what you don't want. So I'm gonna, yeah. So that's just like a basic object. Like if you could only know how to parameterize one object, that's probably the one thing. If you only had to like, if your brain could only store one thing to parameterize, this is the thing that I'd say. And then another thing is and the second object is circles. I'll say the circle of radius r centered at AB has the following parameterization. It does is r of t equals r cosine of t plus a, comma, r sine of t plus b. Okay. And then your t could go between 0 and 2 pi. And if you wanted to just do an arc of that, you could change the bounds, and these would change accordingly depending on like what angles you want to include and delete in your range. So that's a good one to keep in mind. And this, if you do it this way, this will traverse the circle counterclockwise. If you want to do it clockwise, and next in this third section of the course, the direction of the parameterization will matter. So if you want, so for a clockwise rotation, all you need to do is flip the sign. So you'll have r of negative t, and this is just r cosine negative t plus a, comma, r sine negative t plus b, and playing with the parity, the even odds. Well, cosine of negative stuff, you can just ignore it. And for sine, that the negatives pull right on out because sine's an odd function. So I just wanted to spend the time just to remind you how to do some of these more basic parameterizations. These are two good ones to know. Okay, I'm gonna move on. I'm gonna do another line integral. Let's see how much time we have. We have about 13 minutes. That's good. Okay, so these scalar line integrals. The first example we did was that green semicircle. Can I go to page 6? Oh no. Okay. It was that green semicircle, and that was a curve in the plane. But all of this stuff works for a curve in 3D. You know, something with an x of t and a y of t and a z of t. So let's do an example where our curve is in 3D. So what happens when you make x r sine of t plus a and y r cosine of t? Okay, that's a good question. So what that does, that's a good question. So if you got some circle doing this thing, that's starting here at time 0. So I'm answering a question that's in the chat. What that does is, because you're flipping the role of x and y, and let's just pretend a and b are 0 just to make it easy, so we're centered at the origin. What that does geometrically is you're composing it with a flip of the big plane. And if you flip x and y, what that does is it flips things over this line. And so your new curve would be a curve. This is a very good question. I like this. Your new curve would start up here at time 0, and you'd move down like this. So you'd be flipping the orientation, and you'd be starting at a different location, but you still get the same thing. Because, you know, if you square both pieces, you'll still get x squared plus y squared equals 1, and you'll still be on the circle. So that was very good questions. So this was this is sine of t, cosine of t. That's that thing. This is x and this is y. Okay, so let us do an example. We are doing we are going to be doing, so this is example 2. We're going to be doing a scalar line integral of a function f over a curve c ds. And I got to tell you what the f is and what the c is, and then we can start parameterizing. Wait, you drew the second circle going clockwise. Yes, yes. That is true because if you think about it, if I take this circle goes counterclockwise. As I flip it over this line, it's now going to start going, it's going to want to move towards that center line. So it is right. This will go counterclockwise. This one goes clockwise. You could check that if you wanted by maybe plugging in 2 points, like plugging in t equals 0 and t equals pi fourths, and just kind of seeing which direction you go. Okay, so let us do this. I haven't told you what f is. So f is going to be, and this is all in 3D, this is going to be x squared plus y squared plus just a z. And c, I'll actually give you the parameterization. I'll give you so c is helicoid parameterized as r of t equals, I'm going to have basically a cosine and a sine, meaning a bird's eye view of this thing looks like just a circle in the xy plane, and then that z component is going to rise up by t. So just to give you a good illustration, we've seen an illustration before, but in the bird's eye view, it really just looks like this circle. But in real life, that's, that's the shadow it makes. This is the shadow, but really it's kind of like rising from the dead. It's kind of coming up out of the page. And I should also tell you that t is between 0 and 2 pi. So this is all the data that we need. Okay, got 9 minutes. Okay, that's definitely enough time to do this integral. It's not that bad of integral at all. So let's first work on this ds, because they gave us the parameterization, and that's nice. We don't have to think of the parameterization ourselves. So let's go ahead and compute ds. To do ds, remember, we're going to have to find r prime, and then we're going to have to take the magnitude of r prime. So let's do that on the next page. And I'll write what r it is again on the next page. So remember, r equals, it's a cosine, it's a sine, and it's a t. So r, if I want to take a derivative, remember it's component-wise derivative, so this is going to be negative sine cosine 1. And to take a magnitude, I've got, I've got to take a square root and add up the 3 pieces squared. So that's going to give me a sine squared plus a cosine squared plus a 1. You can see that's just going to give us the square root of 2. So again, this is kind of nice. It's not, I don't think it's always going to be the case that this, in theory, this does not depend on t. This is a constant. But in the previous problem, we also had that this was a constant. This was the constant function 1. So, beware, this won't happen every single time. That I don't want to say that happens, but in very nice cases, when it happens, this happens when your curve is moving at constant speed. Hopefully that should kind of make sense. So this tells us that ds is merely root 2 dt. And the last thing we need to do is remember f, I'll write it again, was x squared plus y squared plus just a single z. But to figure out the composition f of r of t, I've got to sub in, like, this is my x of t. I got to sub in this into this, this into this, and then let's do red, this into this. So to get a single function of t, this is not too bad. I'm just going to get the blue substitution is a cosine squared of t, plus that green substitution is a sine squared of t, and subbing into that z gives me what now? Just a t. And that's just 1 plus t. So thus, we can do the integral of f along the curve c. I have my three pieces. We're going 0 to 2 pi. I've got my f, which is 1 plus t. And then I've got my ds, which is root 2 dt. Okay, and yeah, let's see. I'm not going to do the integral because y'all, I know every single one in this class can do this integral. And I'm just going to write the final. Did I do the final answer? Okay, the final answer is, I believe, I did this on my own last night. I think it should be root 2 times 2 pi plus 2 pi squared. I believe that's correct. Okay. And because I just want to say two things and then I'll be done. I didn't get to my last example, but we can probably do that on Monday. So I just want to say something kind of cool. Two things. So here's page 12, is that to try on your own, if you'd like. So redo same integral, which is the integral of c f dA, but instead use, I'd like you to use, instead, I want you to use r of t is the same, essentially the same stuff. I'm just gonna, every time I see a t, replace it with a 2t. So this is cosine of 2t sine sine of 2t comma 2t. And to compensate, because you're going twice as fast, you'll start at 0, but you'll only need to go up until pi. So this traces out c, and if you actually compute this thing using this parameterization, using the times 2 speed, you'll get the same answer. And kind of the philosophy behind that is that, well, okay, to say this in math language, this is saying value of the scalar line integral is independent of choice of parameterization. Okay, and the last thing, and the reason why it works out is, basically, morally speaking, it's like if two people are in two different cars and they're traveling along the same road, and as long as nobody kind of goes back and forth a couple times, as long as both people, they start in Houston, wind up in Dallas, and they took the same road and never backtracked, they've gone the same exact distance. It doesn't matter if the first one's like a speed demon and the other one's a slowpoke. They'll travel the same distance. The road is the underlying geometric object, and the R of t is sort of an auxiliary thing helping you compute the distance, but it doesn't change the distance. The type of car you're using doesn't determine the length of the road, is basically what all this is saying. And the last thing, I know I've only got 2 minutes, this is page 13. No, are we stuck? We are stuck. Oh, good. Okay. The last thing I just want to say is that, remember, this is no more math. You can kind of tune off for a second. Remember, did not remember the double integral of r. If I just integrate 1 dA, this gives area of r. If I do the triple integral of the function 1 dv over the region omega, this gives the volume of omega. So in the last minute, can anybody guess what the single integral of the constant function 1 is along the curve C? Once someone gets this, then we can all be done for the day. Yes, that should be the length of the curve. Yes, arc length or length of the curve. Length of C. Perfect. All right, I'm going to turn off the recording, and then I'm going to stop recording.